All right, so we're finally up to objective B, and we're looking at basically A and B sub-objectives here today. Yeah, that's right. So electrostatics with conductors, right? We want to understand what the nature of electric fields in and around conductors, so you can explain the mechanics responsible for the absence of electric field inside a conductor, and know that all excess charge must reside on the surface of a conductor. We want to explain why a conductor has to be in equipotential, and use it to analyze what happens when we connect conductors by wires. We want to be able to show that all excess charge on a conductor must be on its surface, and so that the field outside the conductor must be perpendicular to the surface. And then be able to describe and sketch a graph of the electric field and potential inside and outside a charged conducting sphere. So those are the objectives for today's lecture. Right, objectives B.1, A and B. All right, so this is basically just 4 principles to remember about conductors, along with a little explanation about why each is true. What does the electric field look like inside of any conductor?
I think it looks like a uniform.
It is uniform, but we can be even more specific than that.
Going from one plate to the other.
Okay. Well, we can see it is uniform, but it's also 0.
Yeah.
Right, the electric field inside of any conductor is always going to be 0. All right, and the reason for that, if you think about it, right, if it's not 0, if the electric field is not 0, that means there's a force on the charges, right? And since you're in a conductor, right? Remember, what makes something a conductor is that the charges, the electrons, are free to move, right? They're not strongly bound to the specific atoms they're on. So if a charge in a conductor feels a force, it's going to move, right? In an insulator, the charges, the electrons are bound to their atoms, so that if there's an electric field on them, right, they feel a force, but then there's also a force that's binding them to the atom, so they can't necessarily move freely, right? In a conductor, the electrons are free to move around, so if there was an electric field, the charges feel a force, and they're going to move, and basically going to move until they get to some equilibrium, right? And once they get to an equilibrium, we know there's no force, so there has to be no electric field. Okay, so whenever you have a conductor, the electric field inside the conductor is always going to be 0. Does that make sense? Questions or comments about that? Okay. The second property of conductors, if a conductor is charged, so if there's any charge at all on the conductor, it's not completely neutral. If the conductor is charged, we can say that all the charge lies on the surface of the conductor, not on the inside of it. And there's a few good ways to go, a couple at least of good ways to go about showing that that's true. But one way to think about it, or to see that this is true based on what we said here, where the electric field inside is going to be 0. If you imagine having a conductor and you draw a Gaussian surface just inside the surface of the conductor, all right? So it doesn't matter if it's a sphere or whatever shape your conductor is, right? If you can imagine a Gaussian surface that's just, infinitesimally smaller than your conductor, so that that surface lines up just inside the surface of the conductor, right?
So can you move the paper down a little bit? Just want to see what was on.
Oh yeah.
Thank you, mister.
So we know that inside the conductor, electric field is 0. Right? So if we draw a Gaussian surface just inside the conductor, we know that the charge inside has to be 0. Right? The electric field is 0 everywhere on that Gaussian surface because it's inside the conductor. And Gauss's law is pretty clear about that. If we know that the electric field is zero, we know the flux is zero, right? There's no electric field lines passing through the surface if the electric field is zero. And since the flux is zero, we know the enclosed charge has to be zero. Right? So since every conductor has zero electric field inside of it, that means that whenever a conductor has a charge on it, the charge has to be on the surface, on the outside of the conductor. Questions, comments about property number 2? All right, you can now do most of those.
The charges are on the surface. That means it can never have flux.
What can never have flux?
Conductor.
Well, when we're talking about flux, right, there has to be a surface that we're talking about, right? So if you were to put the point with this is, let's say we could have a weird shaped conductor. Let's say here's a big piece of metal conductor shaped like this, right? And we know that there's some charge, a coulomb of charge or so on it. But the way this works is we draw a Gaussian surface that's just infinitesimally smaller, just on the inside. Right, and we know that there can't be any flux through this little dotted line surface that I'm drawing now, right? I know there's no flux here because this is inside the conductor, and the electric field is zero at every point inside the conductor, so there can't be any electric field lines passing through this surface. Since there's no electric field lines passing through this surface, the flux is zero, and the enclosed charge has to be zero, right? So if we look at the actual surface of the conductor, right, there might be some flux there, and in the next point we'll kind of see that. But the point is, since inside the conductor electric field is zero, no enclosed charge means no flux, means all the charge has to be on the surface. So that's kind of inside the conductor, right? Electric field is zero. There's no charge inside the conductor. So what we can tell from that as well, our third property of conductors, outside of a conductor, we can say that the electric field is going to be perpendicular to the surface. So for the direction, it's perpendicular to the surface of the conductor. And with magnitude, we also know the magnitude of the electric field is going to be sigma over epsilon naught, and where sigma is the surface charge density. All right, so how many, coulombs per square meter are there on the surface of this conductor at a given point? All right, and the way we can see that is you draw a Gaussian surface with one end inside the conductor and one end outside the conductor. All right, so we can draw this. Let me draw this same kind of weird shaped conductor, blob of metal, right? And if I want to know what the electric field is right at this point, I'll draw a little Gaussian surface here, with part of it inside and part of it outside. Maybe there's a few shapes you could use. I'll try a cylinder here. All right. So I know that the end of the cylinder, if it's inside the conductor, is not going to have any flux passing through it. I can say that the electric field is going to be perpendicular to the surface, so the kind of round barrel of the cylinder isn't going to have any flux through it. All the flux is going to be just through this end of the cylinder here, right? It's outside the surface. So we know that this electric field that's there times the area of this, little circle or whatever shape it is our enclosed charge over epsilon naught. And the amount of charge enclosed is just going to be the charge per area times the area of that circle, or of that piece of the Gaussian surface. Right, so what we have is E times the area is sigma times the area over epsilon naught, and the area cancels out, right, which is good because it shouldn't depend, the electric field shouldn't depend on the imaginary surface that you pick. So what we end up with if areas cancel out is that the electric field is just the surface density divided by epsilon naught. So any conductor you have, if you know the surface charge density on the conductor, you can say what the electric field is at that point. Right, for the magnitude and the direction, it's always going to be perpendicular to the surface.
Mr. Marcus, so would the charge density in a conductor on the surface, would it be the same throughout the whole thing?
That's a good question. We don't know that for sure yet. And the answer is no. It's not going to be the same. And what we're going to see is that you kind of have, the more curvature you have. So see kind of this point of here, and we'll get to why that is in another lecture. But you're going to have kind of more charge built up on these highly curved parts than you will on kind of a flatter part. And we'll see why that is another time. That's a good question, but no, this doesn't need to be uniform, right? You can have different charges built up on different areas of the surface, and in the end, we're going to see it's dependent on how curvy that part of the conductor is. If you have something even like a perfect sphere, then it'll always be the charge will be evenly distributed over it. Okay, good question. Are there questions or comments on the third property of conductors? All right, and finally, the last thing to know about conductors, all points on or inside of conductor are equipotential. They're all at the same potential. All right, any point on your conductor is always at the same potential. It's easy. That's kind of easy to see for the inside part of the conductor, right? There's no electric field. An electric field is the derivative, the slope of the potential, right? So if there's no electric field, that means there's no slope for the potential, so the potential is constant. It's a little harder to see that that's true on the surface, but even points on the surface of a conductor are going to be at the same potential as points inside the conductor, right? And one way to see that, I don't know if it's the clearest way, but one way to see it is remember that to get the potential, you integrate between 2 points, right? If we wanted to find the potential difference, this should actually be a delta V. If we want to find a potential difference maybe between this point here and this point here, right? We would take a path, any path, right, along the surface from A to B. We would look at the electric field at every point, take the dot product of the electric field with the direction along the path, right, and add them all up, right? So that's a tough integral to actually do in the general case. But what we can say is that if A and B are both points on the surface, then we can say that the integral, or not the integral, but every single time we do, or at every point that we do the E dot ds is going to be 0, right? And that's just because E is always perpendicular to the surface. So if E is perpendicular to the surface, right, it's going to be perpendicular to the path as well. So also perpendicular to path ds. Right, you're never going to have a component of the electric field that's in the same direction as the path that you're traveling along to get from point A to point B on your surface. So if E dot ds is always 0, this integral is always 0, so your delta V is always 0. So every point on the surface of your conductor is going to be at the same potential. And those are the 4 properties of conductors that you need to know for the AP E&M test. Questions or comments about the last one or about any of them?
Show me the third property.
Yeah, the third one gives you the electric field just outside of a conductor, right? So at the surface or just outside the surface, right? We know that it's got to be perpendicular to the surface, and we know that the magnitude has to be the charge density divided by epsilon naught.
I see.
And this result, right? This matches up exactly with what we got for just an infinite plane, right? An infinite plane of charge. Although in that case, we got 2 sigma because we had, in that case, we kind of assume a very flat plane so that the charge is kind of not spread out on one side or the other. But if we have a surface that has some finite thickness, right, half of the charge will be on, one side of the slab, half of the charge will be on the other side of the slab. So that's why we don't have a factor of 2 here, but we did for our infinite plane of charge. Other questions or comments on the properties of conductors? This is all in the Survey and Jewett reading as well. But these basically you do want to know these pretty well for the AP test. Right. Let me go back one more time to the objectives now that we've actually looked at them. Oops, here. I should share it. All right, so we can explain the mechanics responsible for the absence of the electric field inside a conductor, right? That was just property 1. And know that the excess charge must reside on the surface of the conductor. That's just property 2. We can explain why a conductor must be an equipotential, which is property 4, and use this in analyzing what happens when conductors are connected by wires. Well, you can kind of take it a step further. If I take 2 conductors and connect them by a wire, which is also a conductor, what can I say about the potential in both conductors? They would have to be the same, right? Because if 2 conductors are connected with a wire, you really just have 1 conductor now. And we know conductors have to be at equal potential. And then we also showed that all excess charge must reside on the surface and that the field outside the conductor must be perpendicular to the surface, and that comes from property 2 that we just saw. All right, and then knowing these properties should help us do objective B again. Describe and sketch what the electric field and potential inside and outside a charged conducting sphere look like. And we'll look at that specifically at another time, tomorrow, or next week. Okay, so I'm going to stop the lecture there for today.